National Educator.
Hello learner, my name is Ted Owiti, and once again a warm welcome to Physics Form 2 lesson. Now today we are going to be tackling Hooke's law, and specifically we will be talking about the spring balance. What is a spring balance? How you can calibrate a spring balance, and some of the applications of spring balances in real life. So let us start with our lesson objectives. So the first objective of our lesson today will be to explain how a spring is compressed using Hooke's law. The second objective is define calibration of a spring balance. And then the third objective is describe how to calibrate a spring balance. And lastly, we will also state the factors that affect the spring constant of a spring balance. Okay, so let's go on. Right away, we're going to start with compressing a spring. So, when the ends of a spring are squeezed together, it shortens. All right? Compressing something is always under compressional forces. When you compress something, you make it to be smaller. So, a spring, if you squeeze the ends, all right, together, it shortens. That shortening, that changing of shape, is what we are calling compression. All right, so you can either stretch something or you can compress it. Now, the forces that are shortening this spring is what we are calling compressional forces, or a compressional force, a force that shortens shortens the length of a spring. So how does the compressional force affect the spring? That is, what is the relationship between the compressional force and the length of the spring? Is it the same as a force that would stretch it? That is what we want to find out. And how do we do this? Well, we'll use the following apparatus. All right, so the following apparatus, or the following setup, is used to study the relationship between the length of a spring and the compressional force that is applied. Notice that we have a load. First of all, we have a spring. All right, it's labeled the spring, and then on top of the spring we have a load. All right, and on the spring is attached a pointer, and the pointer runs along a scale. All right, so the object of this would be, you note the position of the pointer before putting the load, recording it down, putting the load and adding the load, all the while taking readings of the load itself and the measurement, okay, or the position of the pointer. Then after that, we will plot a graph of length against the compressing force of a spring. Now, when we do this, this is the kind of graph that we get. Notice that on the vertical axis, we have the length, all right? And on the horizontal axis, we have the compressing force. Now, we also notice that there is a straight line, okay, with a negative gradient. When the length is very high, the compressional force is 0. But as we increase the compressional force, the length of the spring keeps on reducing. And it reduces in equal amounts. In short, a change in force, okay, will result in the same change in the length of the spring, which means that the compressional force is directly proportional to the length. Is inversely proportional to the length. In short, as the force increases, all right, the length decreases in equal amounts. All right, so if we had a force of, let's say, 1 Newton, and the length reduced by, let's say, 2 centimeters, then if we put another force so that we have a force of 2 newtons, then the length will also decrease by a similar amount as the first one. All right, so that is why we have the graph, and still looking at the graph, we can see that at the end of the line, the straight line, we have a point labeled E. Now, this is the elastic limit. Now, at this point on, you notice that we have a straight line, meaning that no matter how much we add, no matter how much we increase the compressing force, then the extension does not change. All right. At this point, the coils of the spring have already touched one another. All right. So the spring cannot shorten any further than that. So what can we conclude about from this setup? All right. Now, the first one is that the spring obeys Hooke's law during compression. Now, the compression of the spring is directly proportional to the compressing force. All right, meaning that the spring shortens in equal amounts when the force is increased with equal amounts. All right, so the compression of the spring is directly proportional to the compressing force. So that is basically our Hooke's law, all right, because Hooke's law states that the extension of a helical spring is directly proportional to the force applied on it, so long as the elastic limit is not exceeded. Now, but on this case where we are talking about a compressional force and a compression, all right, we are talking about the length shortening, whereas the compressional force increasing. Okay? And then at point E, beyond point E, the spring does not obey Hooke's law. Why? Simply because the coils of the spring are now in contact and the spring cannot be shorter anymore. So what is the importance of all this? All right. Now, for starters, we can use this concept to design and manufacture some equipment that we use in everyday life. For example, we have what we call a top pan balance. I am sure you have seen this in your laboratories, and you can see that it is a device that is used to weigh or get the mass in the, getting the mass in kilograms, or even getting the weight in newtons. All right, so that is one application. The other one is a shock absorber. Now this is a shock absorbers are commonly used in vehicles that are in motion, like motor cars, motorbikes, and the like. So these ones act to reduce the bumpiness of the road that the vehicle is traveling in, and it depends on the compression of a spring. So that is the first part of our lesson, which deals with compressing a spring. The second one is we are going to go straight to a spring balance. So a spring balance. What is a spring balance? A spring balance consists of a spring fixed with a hook on one end and fixed on the other, on the opposite end. And it works on Hooke's law. All right? So it works on Hooke's law. A spring balance scale is usually calibrated in newtons. All right? And it measures weight and not mass. That is a spring balance. But before we can use a spring balance, we need to calibrate it. All right? We need to calibrate it. So what is calibrating a spring balance? Now, calibrating a spring balance is simply the process of putting a measuring scale on the spring balance so that its pointer can align with the mark showing the actual weight that is hung on the hook. All right? So basically, it is coming up with a scale, an accurate scale that is going to enable us to read directly when we look at the scale or the pointer, to read directly that this object that we have hung here weighs a certain amount. So how do we do that? But before we do that, let us go through some of the parts of the spring balance. So this here is a diagram of the spring balance. All right? And you can see that the main component of a spring balance is, of course, a spring. All right? So the spring is attached on one end, and on the other end there is a pointer. So in this particular case, our pointer is actually black in color, if you can see that. And next, it has a uniform scale. All right? So the uniform scale is calibrated, and that is exactly what we are going to do. It is a uniform scale such that because the spring balance actually works on Hooke's law. All right? And lastly, we have a hook that is where we hang objects that we want to do what? That we want to measure the mass. Okay, so let us go straight to the process of measuring, or rather of calibrating the spring balance. The first thing that we need is a blank paper, all right, on a meter rule. Okay, so then of course we need a spring. All right, the spring should be attached to some fixed at the top so that it hangs. All right, and at the end of this, on the pointer, I mean on the spring, we attach a pointer and make it to run along the blank piece of paper that we have attached on some board or even a meter rule. All right, then we need a mass of, let's say, 100 grams. All right, so what is the first thing that you do? The first thing that you do is you will mark the initial position of the pointer. You mark the initial position of the pointer before the spring does what? Stretches. All right, then the second thing that you're going to do is you are going to add the 100 gram mass so that it pulls on the spring, and the spring will, the pointer, we will take note of the final position of the pointer, and we will mark it. All right. And then the next thing is that we will divide the length between the initial mark and the final mark. We will divide it into 10 equal parts. And of course, the initial mark will be our 0 newtons, and the final mark will be our 1 newton. And in between, we can take readings of the any object that has a weight between 0 and 1 newton. All right. So we can use this method to calibrate any form of any number of springs that we want, so long as we know the spring constant. All right, or rather, we don't even have to know the spring constant, just the initial mark and a known weight, like let's say 1 newton or 2 newtons, yeah, so that when we hang it, then we can divide it into the number of equal parts. Remember, the scale of a spring balance is uniform. Okay, so that is calibrating a spring balance. I hope you try it at home, so that you can actually measure some, you can try it out and measure some unknown weights. Now, I want us to proceed on to the next part of our lesson, which is on factors that affect the spring constant of a spring balance. Factors that affect the spring constant of a spring balance. Right. So we have a number of factors. All right. We have a number of factors. And we will be talking about one factor at a time, holding all the other factors constant. All right. What do I mean by this? Okay. Let's look at the factors. Now we have the factors are listed like the length of the spring, the number of turns per unit length, all right, the nature of the material, all right, the diameter of the spring, all right, the diameter of the wire making the spring. So we have at least 5 factors. So what do we mean by holding all other factors constant? This means that when we are talking about the length of the spring, all the other factors below will be constant. They will be not changing. So the only thing that will be changing is the length of the spring. Okay, so how does the length of the spring affect the spring constant? Now, when you put 2 springs in series, one underneath the other, so that they are in a series formation, then we know that the spring balance, the spring constant actually reduces. Why? Because the 2 springs will each extend and carry the weight of the same object. So we will have double extension. Now we can use the same principle here. We will say that, when we are talking about how the length of the spring affects the spring constant, it is such that the longer the spring, all right, the longer the spring, the less the force, the less the spring constant. Okay. Then the other factor is the number of turns per unit length. Now this simply means the number of turns within the unit length of a spring. So you can have a spring with 10 turns per centimeter, and another one has 5 turns per centimeter. So the one with 10 turns per centimeter will stretch more, which means will stretch more than the one of 5 turns per centimeter. All right, and this will make this makes the force constant, or rather the spring constant of the one with the more number of turns to be less than the spring constant of the spring with the number of turns that are less. The other one is the nature of the material. Of course, we know that we have different materials that make up different metals. We can have copper, we can have tin, we can have aluminium. So if we make the nature of the material really determines the spring constant. Some materials that are naturally stiffer than others are going to have a spring constant that is higher than the rest. And then we will also, the next factor is the diameter of the spring. The spring that has a bigger diameter will have a lower spring constant than that of with a smaller diameter. So if you have one that is very big and one that is very small, all right, the one that is very big will have a lower spring constant, which means it will stretch more under the same force. And then, having talked about the diameter of the spring, what about the diameter of the wire? Does it affect? Yes, it does. The diameter of the wire making the spring. A spring made of thicker wire will have a larger spring constant than one that is made from wire with a smaller diameter. Okay, so there you have them. Those are the 5 factors that affect the spring constant of a spring, and by extension the spring balance. So let's look at some of the some activities that I had prepared for you so that we can enhance our understanding of what we had been talking about. So activity number 1, we have a graph, all right, and this graph was drawn from an experiment that was performed to see or to study the relationship between the compressional force and the length of the spring. Okay, so the first thing that we are supposed to do, draw a diagram of the possible setup of the apparatus. Draw a diagram of the possible setup of the apparatus. Secondly, state the range of the force over which the spring obeys Hooke's law. State the range of the force over which the spring obeys Hooke's law. Thirdly, suggest a reason for the shape of the graph between 80 newtons and 120 newtons. Okay, so we already seen the graph. So the possible diagram is of the setup is as shown. We have the load being on top of the spring and the pointer running along a scale as we add more weight. So state the range. Of course, the range would be the range where we have constant gradient, and the range where we have the constant gradient is 0 to 40 newtons. All right, and then suggest a reason for the shape of the graph between 80 newtons and 180. Of course, in this case, we know that it is because the coils of the spring are all in contact and the spring cannot be made shorter anymore. And the second activity are on the spring. It's the spring balance itself. So name the parts that are labeled S, P, U, and H. Okay, so of course S is the spring, all right. Then P is the pointer, U is the uniform scale, and H is of course the hook. So we are nearing the end of our lesson. So let's talk about the task that I have for you today. The task at hand is explain how the following factors affect the spring constant of a spring balance. Explain how the following factors affect the spring constant of a spring balance. And then, of course, we have the factors: the length of the spring, the number of turns per unit length, the nature of the material, the diameter of the spring, and lastly, the diameter of the wire making the spring. Okay, so we've come to the end of our lesson. So thank you very much for joining us, and until next time, bye-bye.
National Educator.